Hello and welcome to this video on adding or subtracting, or a combination of the two, adding or subtracting radical expressions, right? So expressions that have a radical symbol in them, roots, right? Radicals are roots, square roots, cube roots, etc. And what you're going to see here is that adding and subtracting radical expressions will be very similar to adding or subtracting polynomials. Remember how when you add and subtract polynomial terms, you can only combine, add or subtract like terms with the same variables raised to the same exponents, right? The same bases and exponents. We have something very similar here when we're dealing with adding and subtracting radical expressions. So my first page, I'm going to discuss, when can we actually add or subtract radical expressions, and then the following pages after that I'll have several examples. Alright, so first I want to talk about the concept of like radicals. Just like, this is kind of like terms when you were adding polynomial terms. Like radicals. Alright. Like radicals are radicals that have the same index Right, so both of them are square roots, or both of them are cube roots. Right, they have the same index and the same radicand, right, the same expression inside the radical symbol. So both of these things. So for example, 3 multiplied by the square root of 2. Right, this is a radical expression, right? It has a radical symbol in it, the square root symbol. And say negative 7 times the square root of 2. So notice in both of these, the index is the same, right? The index is 2, right? They both have square root radical symbols, so the index is 2. And the radicand, right, the expression inside the symbol, is also 2 for both of these. Alright, so these, 3 times the square root of 2, and this other radical expression, negative 7 times the square root of 2, these are considered like radicals. Alright. Now I think it's hopefully pretty easy to just determine whether or not two radicals are like or unlike. So how about this? 4 times the cube root of 7. Alright, so there's a cube root symbol, radical symbol, and the radicand is 7. And how about negative 5 times the cube root of 4. Right, they're both radical. Right, they're both considered radical expressions. They have a radical symbol in them, that root symbol. Yeah, the index is the same for both of them. Great, right? Both have an index of 3, but this has a radicand of 7, and this has a radicand of 4. Not the same, right? So they have the same index, great, but not the same radicand. So these two radical expressions are not like radicals. Right? So you have to pay attention. Right? Do they have the same root symbol and under those root symbols, radical symbols, do I have the same expression underneath? Do I have the same radicand? Okay. Now, the reason this is brought up, what does it mean for two radical expressions to be like, is because when you add and subtract, when I'm asked to add and subtract radical expressions, you can only combine, and by combine I mean add or subtract, like radicals. Right, so it's very similar to, as I mentioned earlier, very similar to when you're adding polynomial terms. You can only combine like terms. Right, so just one quick example here. I'll do an example of where we can and an example of where we can't, and then we'll get into the further examples, the more complicated ones. So earlier, if I took these guys up here and I said, take 3 times the square root of 2 and add to it, negative 7 times the square root of 2. Well, if you're adding a negative, that's just subtracting. So subtract from that, 7 times the square root of 2. If I take my two like radicals from earlier, you can actually combine these. And the way you do it is, again, very similar to how we looked at combining like terms in polynomials. You see how both of these terms, there are two terms in this expression. Remember, a term is a product separated by a plus sign. So there's 3 root 2 plus and then negative 7 root 2. You see how they have this square root of 2 as a common factor? So if you'd like, you can factor out that square root of 2, pardon me. I factor out the square root of 2, right, the factor that they have in common, that radical that they have in common, that like radical. And then if you pull out a factor of the square root of 2, look at what's left, right? You have 3 minus 7. Right? And what do you get when you combine? 3 minus 7 is negative 4. So I have the square root of 2 times, negative 4. But very often, as I've done in these terms up here, very often a non-radical factor will be put in front of the radical one. So just rearranging these here, this is equal to negative 4 times the square root of 2. Right. And we can always, of course, double check this result with a little calculator work here. Here I have 3 times the square root of 2, and then minus 7 times the square root of 2. And you see it's giving me this negative 5.656 number. And try this down here within the box, the negative 4 times the square root of 2. And indeed, it is the same thing. I guess another way you could say this too is, you could say, well, I factored out square root of 2 and then combine what was left over. Or you could think of it this way, where you keep the like radical as a factor. Right? I keep the like radical, and then the other factor is, just combining the coefficients of the radicals, right? Because look, if I keep the square root of 2, right, the like radical, and then this negative 4 is just what I get when I combine the numerical, the non-radical parts, right? 3 minus 7, negative 4. You can think of it that way as well. I'm going to continue to do the factoring out thing just because I like seeing it and showing it. But if you want to do a little shortcut, again, you can keep the like radical and then just combine the non-radical parts, the non-radical coefficients. Alright, and then one other example on this page before we get to some more complicated ones. What if I asked you to add these two, right? Which would be like subtracting, because again I'll be adding, or let's just write the other order. How about I take negative 5 times the cube root of 4, and then add to that plus, and then this other radical term I had up here, 4 times the cube root of 7. And I said try, what's the sum of these two? Well, as mentioned on the previous page, these radicals are, not like. They don't have the same index and the same radicand. Well, they have the same index, but they don't have the same radicand, right? And they have to have both the same index and same radicand to be considered like. So because they're not like, this is it. You cannot add these. This would be considered as simple as it gets. You would just leave it like this. Don't put the -5 and the 4 together. There's nothing to factor out, right? They don't have any common factor. So just, leave it as is. Just put it in a box, I'm done. Right? Nothing to simplify, nothing to do. All right. Okay. All right. So here's how we're going to approach addition and subtraction of radical expressions. All right. So one more page here, just real quick. So adding or subtracting radical expressions, I'm going to follow the following steps. So adding or subtracting radical expressions, or I'll just say radicals. All right, the first thing I'm going to do is, and I've put up a video on this in the past, all right, so you can look that up, is simplifying the radical expressions first. Simplify the radicals. So simplify all the radicals first. Then add or subtract like radicals. And that's it. All right, it's really going to be that simple. Sometimes it's hard to see, how to simplify a radical. Again, I've put up, please look up other videos, maybe from me or other people on simplifying a radical, simplifying an nth root. All right. But this is it. I'm going to follow these two steps for every single one of these examples I'm going to show you here. Alright, so I'll keep those at top for now. Alright, my first example, and I have the same instructions for every single one, are the instructions are add or subtract, as indicated. If I have a plus sign or a minus sign, I'll add or subtract respectively. Okay. Alright, so this expression has a variable in it, right? The letter y. So very often I like to put, most of the time I remember to do this right away. If there's a variable or variables in an expression, off to the side, I do like to state the domain of the expression. Remember, the domain is just what am I allowed to plug in for my variables. So here I have 9 times the square root of, and the radicand here is 13y. Plus, I'm adding to this term, this product, 4 times, and then again the square root of 13y. So notice they both have the square root of 13y. Now that is an even root, right? That's a square root. And remember, for even roots, if we want a real number output, the radicand can't be negative. So 13 is not negative, that factor, but y can be negative, and I don't want that. That's bad. That'll be a non-real result. So y has to be non-negative is what I'm seeing. All right, so just doing a little thinking about what even roots mean and what we do with even roots. Need to have a non-negative radicand so that we get a non-negative real result. The value of y has to be greater than or equal to 0, or we could say that y has to be non-negative, right? Okay, so later when I go to plug in a value for y, I just know that I'm not going to plug in any negative numbers for y. Simple as that. Okay, So, looking at these two terms, they both have square roots, right? So they both have an index of 2, these radicals, and they both have the radicand of 13y. So these are like radicals. Additionally, I can't, the square root of 13y, when you're taking the square root, you're looking for factors that are perfect squares in the radicand. 13 is prime and definitely not a perfect square. And y is, to the first power, so you can't pull off any perfect squares from that. So step 1, simplifying the radicals. The square root of 13y, that's already as simplified as it can get. So now I'll do the next part, the adding or subtracting of the like radicals, if there are any, and there are here, right? Both of these are like. So as I did in the previous page, again, I like to do this. I'm going to factor out that like radical, the common radical, right? The square root of 13y, factored out. And if I factor out that common radical, what's left over is the 9 plus the 4. All right. Again, just reversing the distributive property. And what is 9 plus 4? It's simply 13. And as I mentioned before, usually non-radical factors are put first, so you can rearrange the order of these and say this is 13, right, the 9 plus 4 factor, times the square root of 13y. Right. And that's it. Right. That's a single radical term now, as opposed to the sum. We had 2 in the beginning, 2 radicals. This is simpler, right, because it only has 1 radical. And of course, you've seen other videos of mine. I like to test my expressions with variables out. So remember the domain here. If this expression I started with is really equal to this expression here in the box, that means that they should have the same value no matter what I plug in from the domain, right? So pick a non-negative number, right? I'm just going to do one test. You can do it many times if you want, check other numbers, but let me pick y to be like 3. All right, I'm just going to put 3 in for y, and I'll use my calculator here to test if these expressions are indeed equal when y is 3. And again, you can do it when y is 5 or 7 or 1,000,000 or 1/3 or any non-negative number you want. Do that on your own. Alright, so I have on this expression 9 times the square root of, and then inside that square root 13 times y, but I'm having y be 3, right? So 13 times 3. Then after that, plus, and then 4 times and the square root of, and then inside that square root 13 times 3 again. All right. So this is the first expression I started with, where y is replaced with 3. And it gives me this crazy value of 81.1849739, blah, blah, right, so on. All right. Now if this is truly equal to what I said, right, they should have the same value if when I plug in 3 for y. So this expression is 13 times then the square root of, and then 13 times y, but again I'm having y be 3 for this particular test. And look, it is indeed the same number, both this 81.184 something. Right. And again, try it out with any non-negative value for y, and they should have the same value, these two. Wonderful. Okay, so that one was nice and simple. The radicals were already like, and I could just combine the coefficients, the numbers in front of them make 13, or do the factoring out like I like to do. All right, well, let's look at my next example. And this next one is just as simple. It's just got 3 terms instead of 2. All right, this one has 3 terms. Pardon me, the 4th root of 5 plus, then the second term, 9 times the 4th root of 5 plus, and then the last term is negative 3 times the 4th root of 5. Alright, so first I'm going to simplify all the radicals. Now, they're all the 4th root of 5, every single one of these radicals. And when you're doing fourth roots, right, remember you're looking for factors of the radicand that are perfect fourth powers, right? Or, bases raised to powers that are multiples of 4. And, the radicand is 5 for all these, and 5 doesn't factor any further. 5 is prime, so I'm not seeing any perfect fourth powers in the radicand. So again, step 1 is done already. I don't need to do anything. All the radicals are already simplified. Step 2 is, add or subtract the like radicals. And every single one of these, right? Every single term has the same radical in it, right? These are all like. They all have an index of 4, right? They're all fourth roots. And they all have a radicand of 5, right? Every single one of those is the fourth root of 5. So, as I said I like to do, I'm going to factor that like radical out. Fourth root of 5, fourth root of 5, fourth root of 5. That is a common factor of all 3 of these terms. So I factor this out. The fourth root of 5 multiplied by, and again it's just reversing the distributive property. So this had 3 terms. I pulled the fourth root of 5 out. What's in parentheses in here should have 3 terms, so that if I were to redistribute the fourth root of 5, I'd get the original statement back. Well, the first term, I removed the fourth root of 5, so technically there's still a factor of 1 there. Right? Anything times 1 is itself. Plus, and then this second term, I remove the factor of the fourth root of 5. There's the 9 left over. Then the last term, I remove the factor of the fourth root of 5. There's the negative 3 left over. And then we can easily simplify what's inside here, right? And that's just combining the coefficients of these fourth roots. 1 plus 9 is 10. 10 minus 3 is 7. And I'm going to do the same thing where I rearrange it, put the numerical factor that's not in a radical first. So this is 7, a factor of 7 times the factor of the fourth root of 5. Great, and that's as simple as that one's going to get, right? And we went from having 3 radical terms down to 1 radical term, much simpler. Right? And if you'd like, you can enter this into your calculator and then enter this into your calculator, and you'll see that they are indeed the same number. I'm just going to do the entering into a calculator when we actually have some variables or some unlike radicals and see what happens. All right, so I'll leave that to you. You can enter that in the calculator, those expressions, and see that they are indeed the same. Okay, another simple one there, because all the radicals were like already. Here's my next example. All right, so we're back to square roots. All right. So I have 2 terms this time. All right, first term is 4 times the square root of 18 plus, and then the next term is negative 3 times the square root of 8. Okay, notice how right now these are not like, right? The square root of 18 and the square root of 8. So at the moment, these are not like, right? The reason being is because they have different radicands, right? They have the same index, sure, they're both square roots, but this has a radicand of 18, this has a radicand of 8, and those are different. So I cannot combine these yet, all right? But, we still haven't done the first step yet. So off to the side here, I'll simplify the radicals, right? Because these actually can be now, this time. So remember the square root of 18. Alright, the square root of 18, you're taking a square root, so you got to think of what's a perfect square. Something that, maybe raised to a power that's a multiple of 2. What's a perfect square? That's a factor of 18. And that'd be 9, right? And you can break up 18 to the perfect square factor times, the non-perfect square factor. 9 times 2 is 18. 9 is a perfect square, right? That's 3 squared. Times, 2 is, 2 to the first. That's not a perfect square. And then using that product rule for radicals, again, if you want to look at a past video on using the product rule for radicals, and break this up into the square root of 9 times the square root of 2. And so we have 3 times the square root of 2. That is equivalent to the square root of 18. All right, so I'm gonna fill that in here in a second. Right? Replace the square root of 18 with a factor of 3 and a factor of the square root of 2. Same thing for square root of 8. Right? The square root of 8, I can simplify that as well. There is a perfect square that goes into 8 evenly, and that would be 4. Right? 4 is 2 squared. So it's the square root of there's a perfect square times a non-perfect square, right, that make up 8. Use our product rule to separate those factors. Square root of 4 times the square root of 2. The square root of 4 is, again, the non-negative square root of 4 is positive 2 times the square root of 2. Right, so I'm going to replace the square root of 8 with a factor of 2 and the square root of 2 with this 2 times the square root of 2. Okay, so let's do that. So my first term now has 4 times, and then the square root of 18 is, remember, 3 times the square root of 2, and I'll write it out with the dots. This is the same thing. So 4 there times, and then 18 is 3 times the square root of 2. There's my first term, and we'll multiply the 4 and the 3. You can multiply your non-radicals and multiply the radicals and stuff. Right? We'll multiply those non-radicals in a second. All right, then minus, or the next term is minus, negative is minus 3 times, right, times, and then the square root of 8 we said is 2 times the square root of 2. Again, I'm using the little dots for the multiplication. All right, so again, the minus 3, and then the square root of 8 replaced with 2 times the square root of 2. All right, so this first term, when you multiply the non-radicals, 4 times 3, that's 12, so I have 12 times the square root of 2 in the first term, plus the second term, you have negative 3 times 2, that's negative 6. We have minus 6 here times the square root of 2. Great. So now after that's step 1, after simplifying these radicals, you can't break down the square root of 2 any further. Look at what we have now. Now the terms have radicals that are like. Right? Both of them have a square root of 2. So I'm just going to write like instead of the full like radicals. Right? These are like radicals. They both have a square root, both have an index of 2, and additionally both have the same radicand as well. So now that I have these like radicals, I'm going to factor that like radical out. Right? The square root of 2 can come out, times, and then what's left over, what remains when I factor out the square root of 2, is 12 minus 6. And what is 12 minus 6? That is just 6. So I have 6 as a factor, times, and then the other factor is the square root of 2. And this is as simple as you're going to get with this example. All right. Now, as I mentioned, I will like to see that indeed this expression is equal to this one, because sometimes it's maybe a little tricky or hard to believe, when these square roots are totally different than this square root down here, and you might think, are they really the same number? Well, I hope they are, and we'll see if they are. I'll use a calculator to help check it for us. So the first expression that I started with was 4 times the square root of 18, then minus 3 times the square root of 8. All right, I get this number 8.485281374, da 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 da. Right. All right, and look at this last expression we ended up with, the totally simplified version. I had 6 times the square root of 2. And 6 times the square root of 2 is indeed the same number, 8.485281374, and so on. Wonderful. All right, that makes me a little happier. I'll believe it a little better. All right. Great. All right, so again, the same 2 steps for every single one. All right, my next one has a variable in it, so again I will talk about the domain of the expression first. All right, so this one's a little crazier looking, right, but it's still manageable. Just follow the same 2 steps. I have -5 times, so the first term, again there's only 2 terms here. The first term has factors of -5, x, and this cube root of 54x. Plus, then the second term, the second product, has a factor of 7 times, and then the cube root of 2x to the 4th. So again, look at them now. These radicals in these terms, right, both these cube roots, yeah, they're both cube roots. They have the same index, wonderful, but they have different radicands, so these are not like. I cannot add these the way they look right now. All right. But again, before I get into all the simplifying and whatnot, because this expression has some letters in it, right, I'd like to think a little bit about what can I plug in for that letter, right? What's the domain? So off to the side here. What's the domain of this expression? What am I allowed to plug in for x? Well, look at these radicals, right? They're odd roots, right? Cube roots. And if you've seen some of my other videos, cube roots, you can take the cube root, you can take an odd root of any number, positive, negative, 0, whatever, right? And the result can be also any real number. So no matter what you plug in for into the radicand, you're going to get a real number back. Right? You don't have to worry about is the radicand negative like you do with even roots. So, and I'm also noticing that there aren't any denominators that could possibly be 0, right? Remember, you can't divide by 0 or have 0 in a denominator. Additionally, there's nothing raised to a negative power. Remember, you can't raise 0 to a negative power because that's basically the same as dividing by 0 when you use that negative power rule for exponents. So it looks to me like I can plug in anything. Right? There are no restrictions here. X can be any real number. All right, so later on when I test, is the expression at the end actually equal to the expression in the beginning? I can plug in whatever I want for x. Wonderful. All right. Okay. So now back to the steps. All right. First step, let's take these cube roots here and simplify them. And again, I'm going to do that off to the side. So simplify the radicals. All right, so I have now the radicals. One is the cube root of 54 times x to the first. And now this time, we're taking a cube root. So I want to think of a perfect cube that is a factor of the radicand that goes into the radicand evenly. And remember, perfect cubes are, things raised to a power, an exponent that's a multiple of 3. So to the 3rd power, the 6th power, 9th power, etc. Well, if you remember your perfect cubes a little bit, I've talked a lot about perfect powers in past videos. 27 is a perfect cube. That's 3 cubed. And that goes into 54 evenly. And that seems to be the only thing in here that has anything that is going to be raised to a power that's a multiple of 3. So I'm going to break up that radicand, the cube, to my perfect cube factor, 27 times, and then 27 times, and then the non-perfect cubes, 27 times 2 times x would give me 54x, right? So there's the perfect cube factor. And then the rest of it, these are not perfect cubes, 2 to the first, x to the first. Then I use that product rule, split this up, that product property. This is the cube root of 27 multiplied by the cube root of 2x. And as I mentioned, the cube root of 27 is positive 3. So this is 3 times, and then the cube root of those non-perfect cubes, the cube root of 2x. Alright, so I'm going to replace this cube root of 54x with 3 times the cube root of 2x in a minute. Alright, then the other one, I have the cube root of 2x to the fourth. Now, the number part, the 2, that's not a perfect cube, right? That's 2 to the first power, and that doesn't factor any further. But the x to the fourth power, now I know 4 is not a multiple of 3, but it does have a multiple of 3 that's less than it, right? I can pull off x to the third power from this, and that's a perfect cube, so I'm going to do that. And if you're unclear about why I'm doing this, I did put up a video in the past about simplifying radicals using the product property to simplify radicals, so take a look at that if you want, or look up other people's videos, or look in your books, whatever. So I'm going to peel off x to the third, right? So there's a perfect cube, and then multiplied by the non-perfect cubes, which would be 2 and then x to the first, right? I need another x to make x to the fourth. So this expression is the same as this one here. Then that product property comes into play. I split the factors up, take the cube root of x cubed times the cube root of the non-perfect cubes, the 2x, and the cube root of x cubed, right? When you take an odd root of an odd power, a perfect odd power, you're just left with the base. It's just going to be x. It doesn't have to be non-negative or anything. Times the cube root of 2x. So I'm going to replace this cube root of 2x to the fourth with x times the cube root of 2x in a second. Alright, so let's do that. So this expression I started with, right, the first term, I have negative 5 times x times, and then replacing, right, the cube root of 54x with these factors of, times 3 times the cube root of 2x. Right, and we'll multiply, negative 5x times 3, that's negative 15x, so I'll put that out front in a second. Plus the second term, got 7 times, and then the cube root of 2x to the fourth, again I'm replacing with this x times the cube root of 2x. Alright. And then actually, simplifying the products out in front of the roots. I mentioned earlier negative 5x times 3, that's negative 15 times x, negative 15x times the cube root of 2x, plus, and then this is simply 7 times x, or 7x out in front of that radical, times the cube root of 2x, and look at what happened to us again, right? After that first step, after simplifying all the radicals, now we look at these terms and the radicals in those terms and see that they are now like. They are both, they both have a cube root of 2x, same index, same radicand. Alright, so just like I've been doing, I'm going to factor out that like radical. So the cube root of 2x comes outside, factored out. And when I remove that factor of the cube root of 2x, I guess I could have also factored out, x too, right? That was also common. So let me do that. Pull out a factor of x as well. I'm sorry that looks kind of crappy. But they also have a common factor of x, if you see that. Right? So they not only do they have the common radical, but they have x as well. So I pull out x times the cube root of 2x. And if I do that, what's left over is negative 15 in that first term, and then there's the positive 7 plus 7 in the second term, and negative 15 plus 7, that's negative 8, and again I'll rearrange it so that's the first factor we write. So this is negative 8 times a factor of x, that common factor we pulled out, and then times that like radical that we pulled out as well, times the cube root of 2x. Great. One single term now, one single product. That is as simple as that is going to get. Alright, and as I like to do, and again, you've seen videos of mine hopefully before this, I like to test a little bit, right? I'm only going to pick one number, but remember, x can be any real number here. These are odd roots. And I just want to check for myself, if this expression truly is equal to this one that I'm saying, then they should have the same value, no matter what I plug in from the domain. This time the domain is any real number. Alright, so this time I'm going to plug in a negative number. Why not? Alright, I can plug in whatever I want for x. So how about negative 7? Why not? Alright, so this first expression, I'm going to go through and replace all the x's with negative 7. So I've got negative 5 times, negative 7 in parentheses here, times, and then the cube root of, and then inside that 54 times, the x is, in parentheses, negative 7. Alright, that's the first term, then plus afterwards. Second term, 7 times, then the cube root of, and then inside the cube root 2 times, and then in parentheses, x to the fourth, negative 7 to the fourth power. Right? All of that inside the radical. Alright, so going through this, replacing all the x's with negative 7, gives me this number, negative 134.9679668, so on. Alright, now again, if these are truly equal, like I'm saying, this expression should have the same value when x is negative 7. So let's see. So I'll go through this one down here in the box. I got negative 8 times, and then x, right, which is replaced by negative 7, times, and then the cube root of, and then inside that cube root just 2 times x, or 2 times negative 7. You see how that took a lot less typing, right? Because it is a simplified expression. It should take less time to write. And let's see. And look at that. They are the same value, both this negative 134.9679668 and so on. And that's just one example, right? That doesn't prove anything, but it is a good test, right? When you say that two expressions are equal, they should be equal for every value of the domain, right? Every value that's allowed to be plugged in. And so try out some other ones. Plug in any other number you want for x up here, down here, plug them in, and you should be seeing the same number twice, right? Okay, let's keep going. Got several more. All right, my next one may be kind of a trick question, but I did mention this before. I brought up an example like this earlier in the video. So here I have, again, two terms again. Right? We're subtracting, adding a negative. Right? We have 7 times the square root of 10 in the first term, plus, and then negative 6 times the square root of 3 in the second term. So if I take the radicals, the square root of 10, is there a perfect square, right? We're doing square roots this time. Is there a perfect square other than 1, right? 1 goes into everything. That goes into 10. Let's see, 1 goes into 10, that's not interesting. 4 is a perfect square, 2 squared. Does 4 go into 10? No. 9 is a perfect square, right? 3 squared. Does 9 go into 10 evenly? No. And then after that, your perfect squares are too large. 16 is too big. So this is simplified already. And so is the square root of 3. Right, the other one, square root of 3, this is also simplified. There is no perfect square other than 1 that goes into 3 evenly. So I cannot simplify these radicals any further. And so step 1's done, and then I'm asked to add or subtract. And then the only things you can add or subtract are like radicals. Well, look at these. these are not like, right? They're both square roots, sure, but they have different radicands, right? One is a 10, one is a 3 as a radicand. So I've already the radicals can't be simplified any further, and the radicals are not like. So you can't do anything. This is it. Kind of a tricky question, right? But I'll just put this in a box. You're done. I can't do anything with this expression. I cannot simplify it any further. All right, so be careful with that too. Just because they throw a problem at you doesn't mean that something needs to be done. Right? Very often they might be trying to trick you into doing something that you shouldn't. Right? Like, ooh, what makes 7 minus 6 is 1, and the square root of 10 minus the square root of 3 is the square root of 7 for some reason. Right? Some people do that very often, but they're, the radicals are already simplified, and they're not like. So you can't do anything. Just leave it. All right, good. All right, I've just got a couple more here for you. So here's another one. I'm doing the same steps. This one has some variables again, so put off to the side the domain. What am I have this variable of z throughout. So what am I allowed to plug in for z? Now, just as a couple examples ago, all of these are odd roots. They're all cube roots. And you can take odd roots of any real number, and the result will be a real number. All right, and then I'm also not seeing any denominators that could possibly be 0. I'm not seeing anything to a negative power where the base could be 0. So just as a couple examples ago, the value of z, right, I can replace z with any real number, right? Z can be any real number. Great, and let's keep that in mind for later. All right, so definitely radicals are not like. Yes, they're all cube roots. They all have the same index, but they all have different radicands. So again, off to the side. Now I'll do these a little more quickly. I'm going to simplify these radicals. I'm not going to write every single little step like the last couple examples. So the first one, you have the cube root of 8 z to the 4th. Well, the cube root of 8, that's 2. Right? 2 to the 3rd is 8. And then remember, we did this with x to the 4th earlier. Z to the 4th I can break up as z cubed times z. And the cube root of z cubed would just be z. And then you'd have a z left over inside the cube root symbol. And that would be the only factor that's not a perfect cube, that z to the 1st. So this simplifies to 2 times z times the cube root of z. All right, the next one. The cube root of the negative 27z. All right, well, negative 27 is a perfect cube. That's actually negative 3 to the 3rd power. So breaking this up, the cube root of negative 27 is negative 3. And then the factor of z to the 1st is not a perfect cube, and I can't pull off a perfect cube like I could with z to the 4th because the power is not higher than 3. So that's still left inside, right, times the cube root of just z. All right, so that's it, negative 3 times the cube root of z for that radical. And then lastly, the only other radical in this expression, the cube root of 125z. All right, well, breaking this up, the 125 is another one of those perfect cubes. That's actually 5 to the 3rd power. 5 times 5 times 5. So the cube root of 125 is 5. And then z to the 1st, just like in this second one, z to the 1st is not a perfect cube, so that's going to stay inside the cube root symbol. Okay, so the cube root of 125z is 5 times the cube root of z. And look at all these. Every single one of them has a cube root of z now, right? So they're all going to be like radicals when I'm done. Alright, so going through this expression in the beginning, alright, this expression should be equal to now. I'm just going to replace all the radicals with what they're equal to over here, right? The cube root of 8z to the fourth, that was this 2 times z times the cube root of z, right? Then we have minus 2 times z times, right, the minus 2z still there. And again, I'm replacing this radical with its equivalent. There was negative 3, right? And again, usually negative factors I'll put in parentheses just to make it look cleaner. But remember, I'm replacing this cube root of negative 27z with negative 3 times the cube root of z. Wonderful. Then plus, and then this last term, the cube root of 125z, that was 5 times the cube root of z. Alright, let's just simplify some of this stuff here. Well, here you got 2z, and that's not changing. 2 times z is just 2 times z, right, times the cube root of z. This next term, you have negative 2z times negative 3. That'd be positive, so it becomes a plus now, positive 6z in front of the cube root of z. And then the last term, nothing really to do there, it's just 5 in front of the cube root of z, plus 5 times the cube root of z. Alright. Now they're all like. Now all the radicals are the cube root of z, right? They all have the same index and same radicand. Wonderful. So I'll factor that out. And there's really, again, now there's not anything else, right? The cube root of z, the cube root of z, the cube root of z. These two have a z factor, but the third one doesn't. Right, and that's it. So the cube root of z is the only common factor to these three terms. So I'm going to factor that out. When I pull the cube root of z out, what's left over? The first term you have 2z plus, the second term you got the positive 6z, and then plus 5 in the end. Okay, now this is not going to be just a number. Alright, this is not going to be just a number. Now if you still want to put it first, fine, but make sure you put it in parentheses, because this is going to have multiple terms, this factor. 2z plus 6z, I can combine those. Those have z to the first. Those are like terms. So that's 8z, then plus 5. Again, put this in parentheses. This whole thing is one factor. All of this is just one factor. Times and then the cube root of z. And there you go. One term, one product. Went from having 3 terms, down to 1 term. A sum of 3 products down to 1 product. Right, there you go. Put it in a box. That's as simple as that's getting. All right, and then just like I like to do, let's test this out. Again, just I do it a bunch of times, but no matter what I pick for z, right? The domain here is any real number. Right? Z can be anything. So I can plug in anything I want for z, and this original expression I started with, this crazy thing, should be equal to what I have down here. Alright, so a nice one to pick would be 8. Let's see that. Alright, let's see when z is 8, right? Because that's a perfect cube, 8. So let's see what happens when z is 8. All right, again, you can pick z to be anything. Try it out with anything, but I'm just trying this one. All right. So the original expression, I have the cube root of 8 times, and I'm having z be 8, so 8 to the 4th power in there. All right, then outside that we got minus 2 times z, so 2 times 8 times the cube root of, and then inside that second cube root, negative 27 times z, but I'm having z be 8. Right? Then plus outside that, And the last one, the cube root, and then inside that cube root, 125 times 8, right? I'm having, again, z be 8. And look at this, 138, a nice whole number this time. I picked 8 on purpose, right, so that we'd have a nice whole number. But when I plug in 8 in this original expression, I get 138 as the value of that expression. Now let's do it down here. So in this first factor, right, in parentheses, I have 8 times z, so 8 times 8, and then plus 5, close parentheses, right, that's all that first factor. Then that times the cube root of z, or 8. I'm having z be 8, and this should be 138 as well, and look, it is fantastic. And try it out with other stuff. Again, it shouldn't just work for 8. It should work for any value in the domain. Right? The expression here should have the same value as this expression in the box down there. All right, great. All right, I have one more example. So far, in every example we've seen up till now, every single radical had the same index. Right? They were all cube roots, or all square roots, or all fourth roots, and so on. In this last example, I have some radicals that don't have the same index. So here I have, the square root of 25m minus 3 times the fourth root of m squared. Notice the different type of root, the different index. This has an index of 2. This has an index of 4. Not only do they not have the same index, they don't have the same radicand either, so they're definitely not like radicals. Alright, so before I get into anything, simplifying the radicals and whatnot, this has a variable in it, the letter m. I'd like to think about what values can I plug in for m. Now, remember, these are even roots this time. Fourth root, square root. And remember, when you're taking an even root, the radicand can't be negative, because if the radicand of an even root is negative, you have a non-real result. So this 25m can't be negative. Well, 25 is not negative, so nothing to worry about there. But the times m part, right? M can't be negative, because if m were negative, you'd have a negative value in the radicand. But it can be non-negative. It can be 0. That's fine. You can take the square root of 0. It can be positive. Same thing over here. Now here, m squared, you can really plug in anything. But because I can only plug in non-negatives here, that's the domain of the entire expression. All right. So the value of m has to be greater than 0 or equal to 0, but not less than 0. And I'll write this in words. M has to be a non-negative number. M has to be non-negative. Right? Okay, so keep that in mind for later when I check, when I do a test of this expression compared to what I write in the end. Alright, so the simplifying the radicals. That first step. Well, one of them is pretty simple. The square root, actually. Right? We have the square root of 25m, that radical. And this one's pretty easy to break up. Now we're looking for perfect squares, right? Square root of 25. 25 is a perfect square. That's 5 squared. M to the first, that's not a perfect square. So that's going to stay inside the radical. So we have the square root of 25 is 5 times the square root of m. And that's as simple as that's getting. All right, so I'm going to replace the first term with 5 times the square root of m in a little bit. The second radical, the fourth root of m squared. Now, some people would say that this is simplified, and I'd agree to a certain extent. we're taking a fourth root here. So what I'm looking for in the radicand are factors that are perfect fourth powers, things raised to a power that's a multiple of 4. Not seeing that in here, right? M squared, that's not a multiple of 4, and it's not even greater than 4. I can't even pull off a perfect fourth power here. But, as in the other examples, all my other examples, I had radicals with the same index. So I'd like it if the radicals had the same index. And I did put up a video recently multiplying radicals. That was multiplying, right? But on multiplying radicals with unlike indices or different indexes, indices. And in that video, we were able to take two radicals with different indices, and change them into radicals that had the same index by remembering this relationship. The relationship between radicals and rational exponents. So remember, when you take the nth root of, say, a to the mth power, or where again this m is not the same as that m. All right. Remember how this is actually an expression that can be written to a fraction exponent, the base of a, to the mth power, and then to the 1 over n, right? When you take the nth root, that's raising to the 1 over n, or the 1/nth power, and then multiplying those exponents, you got a power to a power. You get a fraction power, a to the m over n power. Like that. So if you keep that in mind, right, you can change radicals that don't have the same index into radicals that have the same index. All right. So look here. This, the fourth root of m squared, yeah, I can't pull out any fourth powers from this, but I can rewrite it. The fourth root of m squared would be equivalent to m to the 2/4 power. But 2/4, that is a fraction that definitely reduces, right? 2/4 is 1/2. And what is another way of stating m to that? Now that I've reduced a fraction, I can change it back to a radical. M to the 1/2 power is exactly the same as stating the square root, not the fourth root, right? Notice the denominator is 2. The denominator is the index. It's the square root of m to the first. Right? Just again, using this relationship here. So the fourth root of m squared, you can actually rewrite as equivalent to the square root of m. Right, and do you see the like radicals now? This is 5 times the square root of m. This is 1 times the square root of m. Both have square root of m. Okay. So again, I would keep this in mind for, when two radicals have different indices, and you would like to, try to get them to have the same index. And again, please, go back to my video on multiplying radicals with unlike indices to see how that could be done in other cases. All right, so back to this. The square root of 25m, that's 5 times the square root of m, minus, and then 3 times the fourth root of m squared we saw is the square root of m. And look, these are like. They both have the square root of m in common. I factor that out. And when I pull out the square root of m, the factor remaining is 5 minus 3. 5 minus 3 is 2. And I'll pop that and be the first factor. 2 times the square root of m. And that's as simple as that can get, right? A single term with a single radical. Yeah. So this weird thing up here where the two radicals have different indices is equivalent to this very, very simple statement, just 2 times the square root of m. Alright, so what I'm going to do is, again, do a little test. I like to do a little test, Remember the domain this time though. I can't plug in negative numbers. Don't try negatives because your calculator is going to come back at you saying error, non-real, right? Because of this first one, you'd have the square root of a negative, and that's not a real number, right? So plug in any non-negative number, something that's not negative. Well, again, just based on the way this last expression looks, I'm going to be kind of nice and put in like, 9, because it's a perfect square. Right? I'm going to replace m with 9 and see what happens up here and down here, and hopefully I get the same thing again. You can try any other number you want. Try any number you want as long as it's not negative. So the first expression, I have the square root of 25 times m, but I'm replacing m with 9. Then after that, minus 3 times the fourth root, right, so a radical with an index of 4, of m squared, 9 squared, right, replacing m with 9. So there's the first expression where m is replaced with 9, gives me 6. That has a value of 6. And hopefully you can see that that is indeed equal to the final thing that we got. 2 times the square root of 9, right, the non-negative square root of 9. That's 2 times 3. That's 6. Wonderful. And again, try it with any other number you want, right, any non-negative number, and you'll see that the value of this expression is indeed equal to the value of the last one we got in the box, 2 times the square root of m. Great. So notice I did the same steps every single time when asked to add or subtract terms that had radicals in them, right? Add or subtracting radical expressions. Simplify all the radicals in the expression, and then add or subtract any like radicals, if there are any. Great. And as I like to say at the end of these videos, do the best you can to learn the material on your own before you go looking for help. I find that people tend to remember material for longer and also remember it better when they've taken the time and the effort to learn it on their own. So, of course, read the material, read through the author's examples, perhaps even try to work out solutions to the author's examples before you read how the author did it, and then go back and compare your work to the author's and see how you did, check, see if you can learn from some mistakes there. Obviously, work on loads of exercises, practice problems, and look up solutions to those whenever they're made available to you. Check your work, just to see, track your progress, see how you're doing. And don't give up on a problem or an exercise after one attempt or even 2 little attempts. Don't give up so easily. Very often in mathematics, several approaches work for any particular type of problem. So if after several approaches at a problem, you're still not understanding how it's working, how to figure it out, maybe you should read the material again, maybe even a third time, more slowly, more deliberately. Take good notes. Because if you've been working on some problems, chances are you have a little better idea as to what the author wants from you, what the author expects of you. So then when you read it again, you'll know better what to look for in the reading. So maybe that second or third time through, you'll see some things that you didn't catch the first time, and it'll make things click that didn't click before, and hopefully make the problems that much easier to work on. All right, but if after that, if you've done several read-throughs of the material and approached a bunch of problems in several different ways, several approaches at problems, and you're still not getting it, then it's not a sign of weakness whatsoever to go out looking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos online. There's loads of those too. Videos like this one, or other ones out there that I'm sure are better than mine, and I guarantee you can find them with relative ease. But just, keep at it. Stay persistent. Keep practicing. Don't give up. And I think above all, and I think the hardest thing too, is to try to stay positive. Try to be positive about the subject. Believe in yourself. just a simple, strong belief structure, confidence in your abilities, even if you're struggling. Struggle, that's where you learn the most, is when you're struggling, when you're failing. You see how not to do things, and then you tweak it and fix it for the next time, and you learn. But it's amazing the difference a mindset can make in the learning experience. If you go into something thinking, I hate this, it's boring, I'm not gonna enjoy myself, I'm gonna be bored out of my mind while doing this, I hate it, I've always hated it. Well, chances are you're gonna be in that mindset the whole time. It's gonna make the experience terrible, and you're gonna stay in that mindset afterwards, and nothing will change, and learning will be hindered. So try to go into it with an open mind. Think to yourself, I'm going to read this today. I'm going to practice these problems. I'm going to enjoy it. It's going to be engaging. I'm going to learn something, take something away from it that's positive for my life, my school, my work, whatever. And maybe even have fun with it. And you'll be surprised at the difference a positive attitude can make in the learning experience. Okay, so stay persistent, keep practicing, stay positive, and don't give up. And I just know you'll get it. Thank you very much for watching.